Here is a number that should make you a little uncomfortable. There are more stars in the observable universe than grains of sand on every beach on Earth combined. Somewhere between 100 billion and 400 billion of those stars belong to our own galaxy alone, and current estimates suggest most of them host at least one planet. That works out to something like 1 billion potentially habitable Earth-like worlds in the Milky Way by itself. Not the whole universe, just our galaxy, just the one we happen to live inside. And after pointing every serious instrument we own at the sky for over 60 years, listening on every frequency we know how to listen on, we have found exactly 0 confirmed signals, 0 confirmed visits, 0 confirmed traces of anyone else out there. Not a whisper, not a blip, nothing. Most people hear that and think it means we're probably alone, and maybe that's comforting, or maybe it's terrifying, depending on your mood. But there's a colder, stranger, far more specific explanation sitting underneath that silence, one that a handful of physicists and economists have been quietly developing for decades. And once you actually understand it, you cannot unhear it. It's called the Great Filter. And it doesn't just ask why we haven't heard from anyone else. It asks something much sharper. What if almost every civilization that has ever tried to reach the stars has died before getting there? And what if the deadliest part of that journey isn't behind us yet? It might be dead ahead, and we might already be walking straight into it. Tonight, we're not just going to explain the Great Filter as some abstract cosmic riddle. We're going to walk through the actual evidence, the actual candidates, the actual math. And by the end, you're going to understand exactly why serious scientists think this single idea might be the most important, most dangerous, and most quietly ignored question our species has ever had the ability to ask. And I promise you, the answer is stranger and more personal than you think. Let's start at the beginning, with a lunch conversation in 1950 that nobody at the table thought would still be haunting physicists 75 years later. The year is 1950, Los Alamos National Laboratory, and physicist Enrico Fermi is walking to lunch with a handful of colleagues, casually joking about a recent wave of UFO sightings that had been all over the newspapers. The conversation drifted the way lunch conversations do, from flying saucers to the possibility of faster-than-light travel to the sheer number of stars in the galaxy. And then, according to the people who were there, Fermi suddenly blurted out a question that stopped the entire table cold. Not a philosophical musing, a blunt, almost childlike demand for an answer. Where is everybody? It sounds simple, almost silly, until you actually sit with the math behind it. The universe is roughly 13.8 billion years old. Our solar system is only about 4.6 billion years old, meaning there was more than 9 billion years of cosmic history before Earth even existed. Plenty of time for other stars, other planets, and other civilizations to form, evolve, and potentially spread across the galaxy, long before we ever showed up. Even using painfully conservative estimates for how fast a spacefaring civilization could expand, using slow sublight-speed technology, patiently colonizing one star system at a time, physicist Michael Hart calculated in 1975 that it would only take a civilization somewhere between 5 and 50 million years to colonize the entire Milky Way galaxy. That sounds like an enormous span of time until you compare it to the age of the galaxy itself. Roughly 13 billion years. 50 million years next to 13 billion is less than 0.5%. It is a rounding error. If even one single civilization anywhere, at any point in the last 10 billion years, had developed the ability to spread between stars, the entire galaxy should already be full of them, and we should be tripping over the evidence. We are not tripping over the evidence. We are surrounded by nothing but silence, and that specific, aching, statistically improbable silence is what physicists and economists eventually started calling the Fermi paradox. A universe old enough, big enough, and fertile enough that it should be teeming with visible intelligent life. And yet, as far as we can tell, using every method available to modern science, it appears to be almost completely empty. Fermi's lunchtime question wasn't really a question about aliens. It was a question about arithmetic, and the arithmetic simply does not add up no matter how many times you run it. For decades after Fermi's question, people tried to attack the paradox from the front, trying to actually calculate the odds that intelligent life exists elsewhere. In 1961, astronomer Frank Drake formalized this into what's now called the Drake equation, a chain of multiplied probabilities meant to estimate the number of currently detectable civilizations in our galaxy, the rate of star formation, the fraction of stars with planets, the fraction of those planets that could support life, the fraction where life actually appears, the fraction where that life becomes intelligent, the fraction of intelligent species that develop detectable technology, and finally, the average lifespan of a technological civilization once it emerges. Multiply all those fractions together, and you get an estimated number of civilizations we should currently be able to detect. The problem, and it's a problem Drake himself openly acknowledged, is that almost every single term in that equation was, for most of its history, a total guess. We had no idea how common planets were until the 1990s. We had no idea how likely life was to emerge from non-living chemistry. We had no idea what fraction of life develops intelligence, since on Earth it happened exactly once, in one lineage, after nearly 4 billion years of life existing in forms with no brains at all. Feed wildly different but individually defensible numbers into the Drake equation, and you can get answers ranging from "we should be swimming in alien civilizations" to "we are probably completely alone in the observable universe." Using the exact same equation, the exact same logical structure, just different guesses plugged into the blanks. The equation didn't solve Fermi's paradox. It just gave everyone a more organized way to argue about it. This is where the story takes its darkest, most interesting turn. Because in 1996, an economist named Robin Hanson, thinking about this exact frustration, proposed something different. Instead of trying to guess every individual probability in the chain, what if we just looked at the final result, the silence itself, and worked backward? If the universe really is old enough and big enough that intelligent spacefaring life should be common, and yet we observe none of it, then somewhere in that long chain of steps, from lifeless chemistry all the way to a galaxy-spanning civilization, there has to exist at least one step that is extraordinarily catastrophically difficult to get through, a bottleneck so narrow that almost nothing that starts the journey ever makes it to the other side. Hansen called this bottleneck the Great Filter, and the moment you understand what he actually meant by it, the entire question of alien life stops feeling like science fiction and starts feeling like something much closer to home. Here's the actual mechanics of the idea, stripped down to its simplest form. Because once you see the shape of it, you can't unsee it in literally every headline you read for the rest of your life. Imagine the entire journey from dead matter to a galaxy-colonizing civilization as a long staircase with roughly 9 or 10 major steps. Step 1. A star needs to form with the right kind of planets around it. Step 2. Those planets need the right chemistry, the right conditions for simple, self-replicating molecules to spontaneously appear, a process called abiogenesis. Step 3. Simple, single-celled life needs to survive long enough and get lucky enough to develop into complex cells with internal structures, something that took nearly 2 billion years on Earth and, as far as we know, happened exactly once in our planet's entire history. Step 4. Complex cells need to cooperate and combine into multicellular organisms. Step 5. Those organisms need to develop specialized structures like nervous systems. Step 6. Some lineage needs to develop actual intelligence, tool use, abstract reasoning. Step 7. That intelligent species needs to develop technology sophisticated enough to be detectable across interstellar distances, radio waves, powerful energy use, industrial infrastructure. Step 8. That civilization needs to survive its own technology long enough to actually expand beyond its home planet. And Step 9. It needs to actually colonize other star systems, becoming a permanent, self-sustaining, multi-planetary or multi-stellar civilization. Somewhere along that staircase, at least one step is so difficult, so improbable, so likely to end in failure or extinction that it filters out almost everyone who attempts it, the same way a security checkpoint filters out almost everyone who doesn't have the right documents. It doesn't matter how many billions of planets start the climb. If one single step on that staircase has, say, a 1 in a billion chance of success, then across an entire galaxy of 1 billion candidate planets, you'd expect, on average, only one civilization to ever make it past that step. That's the Great Filter. Somewhere on that staircase between dead rock and galactic empire, there's a step almost nothing gets through. And here's the sentence that should genuinely unsettle you, the one that turns this from an interesting thought experiment into something you actually have to sit with. We don't know which step it is. We don't know if humanity has already passed it, or if it's still somewhere out ahead of us. And depending on the answer, our entire future, whether we're looking at an open, boundless cosmic destiny or a countdown clock we can't see, hinges entirely on which side of that filter we're currently standing. Let's start with the hopeful version of this story, because it deserves a fair hearing before we get to the darker possibility, and it's called the filter is behind us scenario. Under this version, the near impossible step on that staircase is something humanity has already somehow miraculously accomplished, which would mean the hardest part of the entire journey is already finished, and our future, statistically speaking, should be relatively open and hopeful. The best candidate for this scenario is the very first step on the ladder, abiogenesis itself, the spontaneous emergence of self-replicating chemistry from non-living matter. Here's why scientists take this seriously as a genuine candidate for the filter. Life on Earth appeared remarkably early, within a few 100 million years of the planet cooling enough to have liquid water, which on the surface sounds like it should mean abiogenesis is easy, not hard. But early appearance and easy odds are not the same thing. Multiple researchers, including biologist Brandon Carter in the 1980s, have pointed out that Earth's history contains only one clear opportunity for abiogenesis to happen through ordinary gradual chemistry, before rising temperatures made the young planet too hostile. And one successful outcome in one opportunity tells you almost nothing about the actual underlying odds. It's the same logical trap as flipping a coin once, getting heads, and concluding the coin always lands on heads. If abiogenesis genuinely requires an extraordinarily specific, extraordinarily unlikely sequence of chemical accidents, so unlikely that it might only happen once in a trillion suitable planets, then Earth simply got extraordinarily lucky, and the vast majority of otherwise habitable worlds throughout the galaxy might be permanently, chemically sterile, forever, no matter how many billions of years pass. We still do not know how life actually began here, despite nearly a century of dedicated laboratory research trying to recreate the process. From the famous Miller-Urey experiment in 1952, which showed that simple organic molecules like amino acids could form spontaneously under early Earth-like conditions, all the way through modern research into self-replicating RNA molecules and mineral-catalyzed chemistry at deep-sea hydrothermal vents. We can get partway there in a laboratory. Nobody has ever managed to actually recreate the full jump from ordinary chemistry to a genuinely self-replicating evolving system from scratch, under controlled conditions. If that jump really is the great filter, then the silence in the sky isn't sinister at all. It's simply the sound of an almost impossibly rare chemical event, one we happen to win the lottery on, echoing across a galaxy of otherwise lifeless, sterile worlds. There's a second, equally serious candidate for a filter that's already safely behind us, and it's arguably even stranger than the origin of life itself. The jump from simple cells to complex cells, an event biologists call the eukaryotic transition. For roughly the first 2 billion years of life on Earth, nothing more complicated than simple bacteria and archaea existed anywhere on the planet. Tiny, single-celled organisms with no internal structures, no nucleus, no organelles, essentially unchanged in basic design for 2 billion consecutive years, an almost unimaginably long stretch of evolutionary stagnation. Then, somewhere around 1.5 to 2 billion years ago, something happened that appears to have occurred only once in the entire history of life on Earth. One simple cell somehow absorbed another simple cell, and instead of digesting it, kept it alive inside itself, in a permanent, mutually beneficial partnership. That absorbed cell eventually became what we now call the mitochondria, the tiny internal power plants that generate energy inside every complex cell in your entire body. including every single one of the roughly 37 trillion cells that make up you right now, reading or listening to this sentence. This single event, sometimes called endosymbiosis, appears to be the foundational moment that made every form of complex life on Earth possible. Every plant, every fungus, every animal, every single multicellular organism that has ever existed, all descended from that one bizarre, freakishly unlikely merger between two simple cells. A merger that, as far as the fossil record and genetic evidence can tell us, happened exactly once in 4 billion years of life existing on this planet. Biologist Nick Lane has argued extensively that this transition might represent one of the true bottlenecks of evolution, an event so specific, so dependent on an enormously improbable combination of circumstances that most planets with simple microbial life might remain permanently stuck at that stage, teeming with bacteria-like organisms for billions of years, never once making the leap to anything more complex, simply because the specific chemical merger required to unlock complex cellular life is staggeringly unlikely to occur by chance. If this is the great filter, it would mean the universe could genuinely be full of simple, single-celled life, quietly existing on countless worlds, without a single one of those worlds ever developing anything resembling a plant, an animal, or a mind capable of building a telescope and wondering if anyone else is out there. Even after complex, multicellular life gets established, there's a third candidate bottleneck worth taking seriously: the emergence of actual intelligence, capable of abstract reasoning, tool use, and cumulative culture. Earth has hosted complex, multicellular animal life for roughly 600 million years, an enormous span of time filled with an almost unimaginable diversity of body plans, sensory systems, and survival strategies. Dinosaurs dominated the planet for over 160 million years, more than 800 times longer than modern humans have existed as a species, and not a single dinosaur lineage across that entire staggering span of time developed anything resembling human-level intelligence, tool-based technology, or written language. Evolution had an enormous amount of time and an enormous variety of raw biological material to work with, and general intelligence of the specific kind that eventually builds telescopes and radio transmitters appears to have emerged clearly only once in one specific primate lineage within the last few 100,000 years. This matters because natural selection doesn't actually favor intelligence by default the way popular imagination often assumes. Big brains are metabolically expensive, consuming roughly 20% of a human's total energy intake, despite making up only about 2% of body weight, an enormous ongoing cost that only makes evolutionary sense under a fairly narrow, specific set of ecological pressures. Countless successful evolutionary lineages, sharks, crocodiles, horseshoe crabs, have persisted essentially unchanged for hundreds of millions of years without ever needing anything resembling human-style reasoning to survive and thrive. If intelligence really does require an unusually specific, unusually rare combination of ecological pressures, social structures, and evolutionary accidents to emerge at all, then a galaxy could plausibly be filled with complex, thriving ecosystems, forests, oceans, entire biospheres bursting with life, without a single one of them ever producing a species capable of looking up and wondering what those points of light in the night sky actually are. Each of these candidates, abiogenesis, the eukaryotic transition, and the emergence of intelligence itself, would be, in its own way, a genuinely comforting explanation for the silence we observe, because each one places the impossibly difficult step safely behind us, something humanity has already, somehow, beaten the odds to accomplish. Under any of these scenarios, our future is open. We've already run the hardest part of the gauntlet. But there's a much darker possibility that a growing number of serious scientists, physicists, and thinkers about existential risk have started to take even more seriously. And it's the version of this idea that should genuinely keep you up at night, because it doesn't place the danger behind us at all. It places it directly, unavoidably, in our own immediate future. Here's the uncomfortable logic behind the filter is ahead of us scenario, and once you follow it all the way through, it's genuinely difficult to shake. Every single candidate we just discussed, abiogenesis, complex cells, intelligence itself, describes something that happened in Earth's deep, ancient past, something we've already survived, something we can point to and say, we got through that. But there's a very different category of danger, one that doesn't belong to deep evolutionary history at all, but to right now, to the specific, narrow window of time a civilization spends between inventing powerful technology and either surviving it or being destroyed by it. And the unsettling thing about this particular danger is that it wouldn't leave any fossils, any ruins, any evidence for a future alien astronomer to find at all. It would simply end the story, quietly, quickly, and completely, at almost exactly the same evolutionary moment every single time on every single planet unlucky enough to reach it. Physicist Nick Bostrom, who has written extensively on existential risk, points out that a species only becomes detectable to the rest of the galaxy at almost the exact same historical moment it becomes capable of destroying itself. Radio technology, the thing that makes a civilization visible across interstellar distances in the first place, emerged on Earth within decades of the invention of nuclear weapons, biological weapons capable of engineering novel pathogens, and industrial technology capable of altering an entire planet's climate. This isn't a coincidence unique to humanity. It's arguably a structural feature of technological development itself. The same scientific understanding that lets you split the atom to generate electricity also lets you split the atom to level a city. The same biotechnology that lets you cure diseases also lets you, in principle, engineer far deadlier ones. Every technological civilization, anywhere, following anything resembling a similar developmental path, would likely hit this exact same narrow window at almost the exact same time. The brief, dangerous period where you have enough power to end yourselves, but perhaps not yet enough wisdom, coordination, or luck to reliably avoid doing so. If this is the true nature of the great filter, it means we are not looking backward at a bottleneck we've already survived. We are standing directly inside it, right now, in this exact century, walking through the single most dangerous stretch of the entire staircase, the one stretch that might explain why a galaxy old enough and big enough to be teeming with intelligent life, instead appears to be a silent graveyard of civilizations that got exactly this far and no further. Let's talk specifics, because this idea stops being abstract the moment you actually look at how close humanity has already come to walking straight through that filter, sometimes by a margin so thin it's genuinely hard to process. On September 26, 1983, a Soviet early warning satellite system reported that the United States had launched 5 intercontinental ballistic missiles toward the Soviet Union. The officer on duty that night, Lieutenant Colonel Stanislav Petrov, was under standing orders to report any detected launch immediately up the chain of command. A report that, under the tense, hair-trigger nuclear posture of the early 1980s, could very plausibly have triggered a retaliatory strike within minutes. Petrov looked at the data, considered that a real American first strike would likely involve far more than 5 missiles, decided the report was probably a false alarm caused by a satellite malfunction, and chose not to report it. He was right. Sunlight reflecting off high-altitude clouds had confused the satellite sensors. One man's individual judgment call, made under enormous pressure with almost no time to think, is a documented, significant reason full-scale nuclear war did not occur that particular night. This wasn't an isolated incident. During the Cuban Missile Crisis in October 1962, a Soviet submarine, B-59, was operating near Cuba and had been isolated from radio communication for days, unaware that the crisis above the surface hadn't yet escalated to open war. American ships attempting to force the submarine to surface began dropping small depth charges as warning signals, but the submarine's crew, exhausted, overheated, and cut off from outside information, believed war might already have broken out. Soviet naval protocol at the time required unanimous agreement from 3 senior officers aboard to launch the submarine's nuclear torpedo. 2 of the 3 officers voted to launch. The third, Vasily Arkhipov, refused, and the launch did not happen. Historians and nuclear risk researchers now widely consider this one of the closest moments the world has ever come to full-scale nuclear war, decided not by presidents or generals, but by a single dissenting vote aboard a single overheated submarine, made by a man most people have never heard of. These are not obscure footnotes. They are 2 of at least several similarly documented near misses across the Cold War alone, each one resolved not by careful institutional safeguards working exactly as designed, but by individual human judgment, sometimes correct judgment made under nearly impossible pressure, sometimes simple luck, standing between the world as we know it and a nuclear exchange that could have killed hundreds of millions of people directly and plunged the rest of the planet into a nuclear winter capable of collapsing global agriculture for years afterward. If a great filter really does exist somewhere in humanity's immediate future, nuclear weapons represent one of its most obvious, most heavily documented, and most historically near-miss-prone candidates. And the uncomfortable truth is that we've already come far closer to walking through it than most people realize. Nuclear weapons are the oldest, most familiar existential risk on the list, but they are far from the only candidate, and in some ways they might not even be the most dangerous one anymore. Consider, engineered pandemics, a threat that has moved from science fiction speculation to documented laboratory capability within just the past 2 decades. In 2011, two separate research teams, working independently in the Netherlands and the United States, successfully modified the H5N1 avian influenza virus to become transmissible between mammals through the air, a property the naturally occurring virus does not have, specifically to study how such a mutation might occur, and specifically raising the uncomfortable question of what happens when the tools required to create a globally catastrophic pathogen become available not just to well-funded, well-monitored government laboratories, but to an ever-widening circle of researchers, universities, and eventually, potentially, individuals as the underlying biotechnology continues to become cheaper, faster, and more accessible with each passing year. The COVID-19 pandemic, whatever its actual origin, which remains genuinely disputed among scientists, offered the entire world an unplanned, unwelcome demonstration of how quickly a single pathogen can circle the globe, overwhelm healthcare systems, and reshape the daily life of nearly every human being on the planet, using nothing more exotic than natural viral evolution. Now consider a pathogen deliberately engineered to combine high transmissibility with high lethality, two properties that tend to work against each other in naturally evolved viruses. Since a pathogen that kills its host too quickly often struggles to spread efficiently before running out of new victims, but a pathogen that doesn't have to evolve naturally, one engineered directly by a research team with sufficient technical skill, could potentially combine both properties deliberately. Creating something nature itself would be unlikely to ever produce on its own. Existential risk researcher Toby Ord, in his extensively researched 2020 book, The Precipice, estimated that engineered pandemics currently pose a significantly higher existential risk to humanity over the coming century than nuclear weapons do, precisely because the barrier to entry keeps falling while the potential destructive ceiling keeps rising. Nuclear weapons require enormous industrial infrastructure, rare materials, and immense technical expertise that remain for now largely confined to nation-states. The tools of synthetic biology, gene editing techniques like CRISPR, and the growing availability of genetic sequencing and synthesis technology are becoming cheaper and more widely accessible every single year, following something close to the same exponential cost curve that made personal computers and smartphones ubiquitous within a single human generation. If the great filter really does sit somewhere in a civilization's near future, a threat that requires only a small number of sufficiently skilled, sufficiently reckless, or sufficiently determined individuals, rather than an entire nation's military-industrial complex, represents a genuinely different, and in some ways more difficult to prevent, category of danger. Then there's the risk that has, in just the past few years, jumped to the very top of many serious researchers' lists: advanced artificial intelligence. This isn't about science fiction robots deciding to rebel against their creators. The actual concern that a growing number of computer scientists and AI researchers, including many who work directly on building these systems, have raised is subtler and in some ways more unsettling than that. It has to do with what happens when we build systems that are extraordinarily good at achieving goals without being equally good at making sure those goals actually align with what human beings genuinely want, a problem researchers call the alignment problem. Here's a simplified way to understand why this worries serious people. An AI system trained to optimize for a specific measurable objective, say, maximizing engagement on a social media platform, or maximizing efficiency in a manufacturing process, will pursue that objective with a single-minded thoroughness that no human employee ever would, exploring strategies and edge cases a human designer never anticipated or intended, simply because the system has no built-in concept of the countless unstated, common-sense human values that a person would naturally respect without ever needing to be told. As these systems become more capable, more autonomous, and more deeply integrated into critical infrastructure, financial systems, scientific research, and eventually military decision-making, the gap between technically achieved the stated objective and did what humans actually wanted becomes a genuinely dangerous space for catastrophic, unintended consequences to hide in, especially once a system becomes sophisticated enough to resist correction or shutdown if doing so would interfere with achieving its objective. In 2023, hundreds of AI researchers, including some of the field's most prominent and most senior figures, signed a public statement declaring that mitigating the risk of extinction from advanced artificial intelligence should be a global priority alongside other large-scale societal risks like pandemics and nuclear war. A remarkable, almost unprecedented moment of researchers publicly warning about the very technology their own careers are built on advancing. Nobody knows, with any real confidence, exactly how dangerous advanced AI will actually turn out to be, or exactly when, if ever, it might cross some critical threshold of capability that makes it genuinely difficult for human beings to remain in meaningful control of the systems we've built. But if the Great Filter really does represent the specific narrow window where a civilization gains enormous technological power before developing the wisdom and coordination to wield it safely, artificial intelligence represents perhaps the newest, fastest-moving, and least well-understood entry on an already crowded and genuinely frightening list. Not every candidate for the Great Filter arrives in a single dramatic moment like a nuclear exchange or an engineered pathogen. Some researchers point to slower, quieter, more grinding threats, the kind that don't end civilization in an afternoon, but instead erode the underlying conditions a technological society depends on until collapse becomes effectively unavoidable. Sometimes over the course of a single human lifetime, sometimes across several generations. Climate change belongs firmly in this category. Current scientific consensus suggests that without significant intervention, global average temperatures could rise enough over the coming century to trigger a cascade of interconnected consequences. Shrinking fresh water supplies, collapsing agricultural yields in some of the world's most densely populated regions, increasingly frequent and increasingly severe extreme weather events, and the displacement of hundreds of millions of people from coastal areas and increasingly uninhabitable regions. None of this on its own is likely to cause outright human extinction the way a full-scale nuclear war or an engineered super pandemic plausibly could. But existential risk researchers worry less about climate change as a direct killer and more about it as what they sometimes call a threat multiplier, a background condition that makes every other risk on this list significantly more dangerous by straining the exact global institutions, international cooperation, and resource stability that would otherwise help a civilization successfully navigate its way through the other. Sharper dangers we've already discussed. A world destabilized by mass climate migration, resource scarcity, and collapsing agricultural regions is a world with less capacity for the kind of careful, coordinated, long-term thinking required to prevent nuclear escalation, regulate dangerous biotechnology, or thoughtfully manage the development of advanced artificial intelligence. In this framing, climate change doesn't need to be the filter all by itself. It just needs to weaken civilization enough that one of the other faster-acting filters becomes significantly more likely to actually finish the job. Toby Ord's careful, extensively researched analysis in The Precipice attempted to put actual numbers on all of these risks combined, and his overall estimate, while explicitly acknowledged as an informed judgment rather than a precise calculation, suggested something genuinely sobering. Roughly a 1 in 6 chance that humanity experiences an existential catastrophe, meaning an event that either causes outright extinction or permanently and drastically curtails our long-term potential, sometime within the next 100 years. A 1 in 6 chance is the same odds as a single pull of the trigger in Russian roulette. Ord didn't arrive at that number to be dramatic. He arrived at it through careful, methodical analysis of each individual risk we've just walked through, and the uncomfortable truth his research points toward is this. If the great filter really does sit ahead of humanity rather than behind us, we may currently be living through the exact century where the outcome gets decided, whether we fully appreciate the stakes or not. Now, let's step back from the darkest version of this story and ask a genuinely important question. Is there actual scientific evidence, beyond pure statistical reasoning, that helps us figure out which side of the filter we're actually standing on? This is where astrobiology, the scientific study of the possibility of life beyond Earth, becomes directly relevant, because every discovery this field makes either strengthens or weakens specific candidates for where the great filter might actually sit. Consider the rare Earth hypothesis, developed by paleontologist Peter Ward and astronomer Donald Brownlee in their 2000 book of the same name, which argues that while simple, single-celled microbial life might actually be quite common throughout the universe, wherever liquid water and basic organic chemistry exist, complex animal-like life requires an almost absurdly specific, almost improbably lucky combination of planetary circumstances to ever emerge and survive. Earth benefits from an unusually large moon, formed by a rare glancing planetary collision early in the solar system's history, which stabilizes our planet's axial tilt and prevents the kind of chaotic climate swings that would make complex, long-term evolution far more difficult. Earth sits within our sun's habitable zone at exactly the right distance to maintain liquid water across billions of years, orbiting a star that is unusually stable and long-lived compared to many other star types. Earth possesses plate tectonics, a geological process that recycles carbon, regulates long-term climate, and may have played a crucial role in generating the chemical diversity needed for complex biochemistry, a process that, as far as we currently know, may not be common on other rocky worlds. And Earth sits in a relatively quiet, unusually stable region of the galaxy, far enough from the crowded, radiation-intense galactic center to avoid frequent sterilizing gamma-ray bursts and nearby supernova explosions, and far enough from the galaxy's chaotic, star-forming spiral arms to avoid the kind of gravitational disruptions that regularly fling comets and asteroids toward inner planets. If the rare Earth hypothesis is correct, it would suggest that complex animal-level life, and by extension, intelligence itself, might represent an extraordinarily rare cosmic outcome requiring so many independent, low-probability circumstances to align simultaneously that most of the galaxy's billion-plus potentially habitable worlds might host nothing more complex than microbial slime, if they host any life at all, placing the filter safely, comfortably behind us in the deep, ancient past, rather than lurking somewhere in our immediate future. But the evidence doesn't all point in that comforting direction, and it's worth being honest about the genuine tension in the data. Since the first confirmed detection of a planet orbiting a sun-like star in 1995, astronomers have identified more than 5,500 confirmed exoplanets. And the picture that has emerged is one where planets, including rocky, Earth-sized planets sitting within their star's habitable zone, appear to be remarkably common throughout the galaxy, not rare at all. The Kepler Space Telescope, which monitored roughly 150,000 stars between 2009 and 2018, found that statistically, nearly every star in the galaxy likely hosts at least one planet, and that Earth-sized, potentially rocky worlds within a habitable orbital distance appear to be a common, not exceptional, outcome of planetary formation. This directly challenges at least one pillar of the rare Earth argument. If Earth-like planets are common rather than rare, the bottleneck, if one exists, has to be located somewhere further along the staircase, in the chemistry or biology of life itself, rather than in the basic planetary real estate required to host it. There's also growing evidence that life, once it exists, might be considerably more resilient and adaptable than scientists once assumed, based on the discovery of extremophiles, organisms found thriving in conditions once considered far too hostile to support any biology at all. Microbial life has been found flourishing in boiling, acidic hot springs, in crushing pressure at the bottom of the deepest ocean trenches, in ice cores buried deep within Antarctic glaciers, and even in a handful of remarkable studies apparently surviving direct exposure to the vacuum and radiation of space itself, in the case of certain hardy microorganisms and tardigrades. If life turns out to be broadly resilient and adaptable once it gets started, rather than fragile and easily extinguished, that pushes against the idea that early planetary conditions represent much of a meaningful filter at all, and pushes the mystery further up the staircase toward the more specific biological and technological steps we discussed earlier. The search for actual biosignatures, detectable chemical evidence of life on other worlds, has also produced a string of tantalizing, if ultimately unconfirmed, hints in recent years. In 2020, a team of astronomers reported a possible detection of phosphine gas in the atmosphere of Venus, a molecule that on Earth is primarily produced by biological processes, though the detection and its interpretation remain genuinely disputed within the scientific community, with several follow-up studies failing to confirm the original signal. The James Webb Space Telescope has begun directly analyzing the atmospheric chemistry of exoplanets light years away, searching for combinations of gases, like oxygen alongside methane, that would be difficult to explain through purely non-biological geological processes alone. As of this recording, no confirmed biosignature has ever been detected on any planet beyond our own. But the tools we now have for looking are dramatically more capable than anything that existed even a decade ago, and the search itself, run by serious scientists using serious instruments, tells you something important. Nobody in this field considers the question settled in either direction. Let's talk directly about the actual search for extraterrestrial signals, because it's worth understanding exactly how much silence we're actually talking about, and exactly how much of the sky we've genuinely covered. The search for extraterrestrial intelligence, or SETI, has been conducting organized radio searches since Frank Drake's original project Ozma in 1960, which spent a few months listening to two nearby sun-like stars for any sign of an artificial signal. Over the following 65 years, the search has grown dramatically more sophisticated, culminating in projects like Breakthrough Listen, launched in 2015 with $100 million in funding, using some of the most powerful radio telescopes on Earth to scan 1 million nearby stars and the entire plane of the Milky Way across a wide range of radio frequencies. And the result, after all of that time, all of that funding, and all of that technological sophistication, has been a complete, unbroken silence, with the exception of a handful of intriguing but ultimately unconfirmed anomalies, the most famous being the so-called WOW signal, a brief, unusually strong burst of radio noise detected by astronomer Jerry Ehman in 1977, matching several of the theoretical characteristics scientists had predicted an artificial signal might have but never repeated, despite decades of astronomers pointing telescopes back at the exact same patch of sky, hoping for a second occurrence that never came. It's worth being honest about the actual scale of what SETI has genuinely searched, though, because it's dramatically smaller than most people assume. Astronomer Jill Tarter has compared the entire history of SETI's search to dipping a single drinking glass into Earth's oceans, checking the water, and concluding there are no fish, when in reality, we've barely sampled a meaningful fraction of the total number of stars, the total range of possible frequencies, and the total window of time during which any given civilization might actually be broadcasting. This is actually one of the more hopeful counterarguments to the darkest version of the Great Filter, sometimes called the temporal dispersion problem. Even if intelligent technological civilizations are relatively common throughout galactic history, the odds that any two of them happen to be broadcasting detectable signals at the exact same narrow window of cosmic time, out of billions of years of galactic history, might simply be extraordinarily small, entirely independent of whether either civilization survives or destroys itself. A civilization might only broadcast detectable radio signals for a few hundred years before switching to more efficient, less leaky communication technology that doesn't radiate obviously into space, the way humanity itself has already begun shifting away from broadcast television and radio toward more contained, cable-based, and fiber-optic communication. If detectable windows are genuinely this brief, the silence we observe might tell us far less about extinction and far more about simple, unlucky cosmic timing than the great filter hypothesis assumes. Not every explanation for the silence requires anyone to be dead at all, and it's worth taking the most unsettling alternative seriously before we move on, because unlike the great filter, this one doesn't assume extinction. It assumes something arguably worse: deliberate, strategic silence. It's called the dark forest hypothesis, popularized by science fiction author Liu Cixin in his novel of the same name, though it's built on a genuinely serious game-theoretic argument that some physicists and thinkers about existential risk have engaged with seriously, not just as fiction. The idea imagines the universe as a dark forest at night, full of hunters, where every civilization is simultaneously a potential predator and a potential prey animal, and where broadcasting your location loudly and confidently, the way humanity has been doing with radio waves for over a century, might be the single most dangerous thing any civilization could ever do. Here's the underlying logic. Because interstellar distances are so enormous, and because civilizations can't easily verify each other's true intentions, capabilities, or values across a gap of potentially thousands of years of light-speed communication delay, any civilization detecting a rival might reasonably conclude that the safest possible strategy is to eliminate any potential future threat before it becomes powerful enough to pose one, especially since a sufficiently advanced civilization might be able to destroy a rival at a distance using relatively simple, hard-to-defend-against methods long before any actual negotiation or diplomacy could ever meaningfully take place across such an enormous communication-delayed gap. Under this theory, the silence we observe isn't evidence that everyone's dead. It's evidence that everyone who survived this long already learned the hard way or through careful theoretical reasoning to stay quiet, to listen without broadcasting, treating the entire galaxy as a place where advertising your existence is an act of reckless, potentially suicidal naivety. A gentler cousin of this idea is the zoo hypothesis, first proposed by MIT radio astronomer John Ball in 1973, which suggests that advanced civilizations might already know we exist and have deliberately chosen not to make contact, either out of caution, out of respect for our own independent development, or as part of some kind of galactic non-interference policy, similar in spirit to the way modern conservationists try to observe wildlife without disturbing its natural behavior. Neither of these ideas requires an actual great filter to explain the silence, and that's precisely what makes them worth taking seriously. Because if either the dark forest or the zoo hypothesis turns out to be closer to the truth, humanity's own instinct to broadcast our presence loudly into the cosmos through decades of unshielded radio and television transmissions, and through deliberate messages like the Arecibo broadcast of 1974, might represent a genuinely reckless gamble, made without anyone ever having the chance to actually vote on whether it was worth the risk. Now, here's where we get into territory that almost never shows up in typical explanations of the Great Filter, but genuinely deserves your full attention because it's one of the strangest, most mind-bending pieces of the entire puzzle. And once you understand it, you'll never think about your own existence quite the same way again. It's called anthropic reasoning, and it starts with a deceptively simple question. Given that you exist right now as a human being living in the 21st century, what can the mere fact of your own existence at this particular moment in history actually tell you about the future of your entire species? This might sound like a philosophical parlor trick, but physicist Brandon Carter and later philosopher John Leslie developed it into something with genuine mathematical teeth, called the doomsday argument. Here's the core idea, and try to follow it carefully because it's genuinely counterintuitive the first time you hear it. Imagine all the human beings who will ever live across the entire past and future of our species as a giant lottery drum, and imagine that you, the person reading or listening to this sentence right now, are a randomly selected ticket pulled from that drum. Statistically speaking, you should expect to find yourself somewhere in the middle of that total population, not at the very beginning and not at the very end. The same way if you reached into a bag of 100 numbered tickets, you'd expect to pull something close to number 50, not number 1 or number 100. Now here's the unsettling part. Roughly 117 billion human beings have ever been born across the entire history of our species. And you happen to find yourself among a very specific, very recent slice of that total population, born after nearly all of human history has already happened. If humanity is destined to survive for millions more years, colonizing other planets, growing into trillions of future individuals across a long, thriving future, then you, statistically, would be an almost impossibly early, almost impossibly rare observer, born in the first sliver of a % of everyone who will ever exist. The same way it would be strange to reach into that bag of 100 tickets and happen to pull ticket number 1. But if humanity's total population across all of time turns out to be much smaller, say, in the range of a few 100 billion to a few trillion people total, because our species goes extinct relatively soon rather than surviving and expanding for millions of years, then your position, born recently, among a comparatively modest total population, becomes statistically unremarkable, exactly the kind of middle-of-the-drum position you should expect to find yourself in. The doomsday argument, when you run the actual statistics, suggests something genuinely disquieting. The mere fact that you exist now, rather than at some far more distant point in a long, thriving future, is itself weak but real statistical evidence that humanity is more likely to face some kind of civilization-ending event relatively soon, rather than surviving and expanding for millions of years into a vast cosmic future. This is not a claim about any specific threat, not nuclear weapons, not AI, not pandemics. It's a purely statistical argument derived entirely from the anthropic fact of your own position in the total timeline of human existence, and it arrives through a completely different logical path, at roughly the same unsettling conclusion the great filter suggests. Something about our current moment in history might be less safe and less permanent than most people casually assume it to be. To be fair, the doomsday argument has drawn serious, legitimate criticism from other philosophers and statisticians, and it's worth presenting that pushback honestly rather than treating the argument as settled fact. Critics point out that the argument depends heavily on exactly how you define the reference class of observers like you, and that subtle changes to that definition can dramatically change the conclusion. Philosopher Nick Bostrom, working through these exact anthropic puzzles in enormous technical detail, proposed a competing principle called the self-indication assumption, which suggests that in a universe where more observers exist overall, you should actually expect to find yourself as one of the more numerous type of observer, a subtle statistical correction that, depending on how it's applied, can partially or even fully cancel out the doomsday argument's pessimistic conclusion. The debate between these competing anthropic principles remains genuinely, actively unresolved among specialists in the philosophy of probability, and reasonable, technically sophisticated people continue to disagree about which framework, if either, correctly captures how we should reason about our own position in time. What makes this genuinely worth including in tonight's exploration, regardless of which side of the technical debate turns out to be correct, is what it reveals about the sheer number of independent angles from which serious thinkers have approached the same underlying worry. The great filter approaches it through astrobiology and cosmic silence. Existential risk researchers like Toby Ord approach it through careful, itemized analysis of specific modern threats. And anthropic reasoning approaches it through pure statistics and probability theory, using nothing more than the mathematical fact of your own existence as the entire data set. Three completely different fields, three completely different methodologies, all circling independently around the same uncomfortable possibility that the window humanity is currently living inside might be considerably more fragile and considerably more decisive than our everyday experience of ordinary, uneventful life ever makes it feel. Let's make all of this feel real, because it's easy to let numbers like 13.8 billion years and 117 billion humans wash past as abstractions rather than something you can actually feel in your body. Carl Sagan popularized a tool for this exact purpose called the cosmic calendar, which compresses the entire 13.8 billion year history of the universe into a single ordinary calendar year, January 1st at midnight, representing the Big Bang. And this exact moment, right now, representing midnight on December 31st. On this compressed calendar, our Milky Way galaxy doesn't form until around March. Our own solar system and Earth don't appear until early September, more than 2/3 of the way through the year. The very first simple life on Earth shows up around September 21st. Complex multicellular life doesn't appear until mid-December. Dinosaurs arrive on December 24th and go extinct on December 30th, at around 6:30 in the evening. Modern humans, Homo sapiens, our entire species, doesn't show up until 11:52 p.m. on December 31st, just 8 minutes before the calendar year ends. All of recorded human history, every pyramid ever built, every war ever fought, every book ever written, every person you've ever loved fits inside the final 14 seconds of that entire cosmic year. And the specific technological era we're living through right now, nuclear weapons, biotechnology, artificial intelligence, the exact narrow window where the great filter, if it exists, would most plausibly be waiting for us, occupies a fraction of a single second at the very tip of that final 14-second sliver. Here is the point of walking through that exercise, and it's not meant to make you feel small in a depressing way, though it certainly can feel that way at first. It's meant to help you actually feel, physically, in your gut, just how recent and how narrow this entire moment in cosmic history actually is. Everything we've discussed tonight, every existential risk, every candidate for the great filter, every anthropic argument about your own position in the timeline of human existence is unfolding inside a sliver of time so thin that on Sagan's calendar it would be genuinely difficult to even draw it with a pen fine enough to represent it accurately. We are not living through some ordinary, unremarkable stretch of human history. Whether we realize it or not, whether we act like it or not, we are living through the single most technologically decisive, most statistically loaded, most quietly dangerous moment our species has ever occupied in the entire 13.8 billion year history of the universe. And here's something that should genuinely surprise you, because it suggests humanity has already brushed up against something disturbingly close to extinction once before, long before nuclear weapons or engineered pathogens ever existed. Roughly 74,000 years ago, the Toba supervolcano, located on the Indonesian island of Sumatra, erupted in one of the largest volcanic events of the last 2 million years, ejecting an estimated 2,800 cubic kilometers of material into the atmosphere, an eruption thousands of times larger than Mount St. Helens in 1980. The resulting volcanic winter, caused by massive amounts of ash and sulfur dioxide blocking sunlight worldwide, may have dramatically cooled global temperatures for years afterward, devastating plant life, collapsing food chains, and creating brutal survival conditions across large portions of the planet. Some geneticists studying human DNA have proposed what's called the Toba catastrophe theory, suggesting that this eruption may have caused a severe population bottleneck in early Homo sapiens, potentially reducing the entire global human population down to somewhere between a few thousand and perhaps 10,000 breeding individuals, based on the surprisingly low genetic diversity found across all modern humans, compared to some other primate species with much larger population histories. Under this theory, every single human being alive today, all 8 billion of us, would be descended from a startlingly small founding population that survived an environmental catastrophe severe enough to nearly wipe out our entire species, tens of thousands of years before anyone was around to write the story down. It's important to note that this specific theory remains genuinely debated among paleoanthropologists and geneticists, with some more recent archaeological evidence from sites in South Africa suggesting human populations in at least some regions survived the Toba eruption's aftermath without catastrophic disruption, complicating the simplest version of the bottleneck story considerably. But regardless of exactly how severe that particular ancient event turned out to be, the broader genetic evidence for unusually low human diversity compared to species with more stable population histories does suggest that our species has, at some point in its deep past, passed through at least one genuinely severe population squeeze, a moment where the entire future of Homo sapiens may have depended on a comparatively tiny number of individuals simply managing to survive long enough to have children. We have, in other words, quite possibly already walked along the very edge of extinction once before, entirely by accident, without any nuclear weapons, without any engineered pathogens, using nothing more dramatic than an unlucky volcano and several difficult centuries of cold, hungry survival. So if the great filter really is somewhere in our immediate future, is there actually anything a species can do about it? Or is this simply a fate we're powerless to influence, discovered only in hindsight by whoever, if anyone, eventually survives it? This question has given rise to an entire genuinely serious field of academic and philanthropic effort over the past 2 decades, sometimes grouped under the term existential risk studies, or more broadly, long-termism, the idea that positively influencing the very long-term trajectory of civilization, potentially spanning thousands or millions of future years and an almost unimaginable number of future human lives, represents one of the most morally significant things anyone alive today could possibly work on. Organizations like the Future of Humanity Institute at Oxford University, founded by philosopher Nick Bostrom in 2005, and the Center for the Study of Existential Risk at Cambridge University, founded in 2012, have spent years researching exactly the threats we've discussed tonight: nuclear conflict, engineered pandemics, advanced artificial intelligence, and climate-related instability, specifically trying to identify concrete, actionable ways to reduce the probability that any of these threats actually materializes into a civilization-ending catastrophe. This work has already produced tangible, if unglamorous, results. International agreements limiting the proliferation of biological weapons, ongoing efforts to strengthen global pandemic preparedness, and early warning disease surveillance systems, following the hard lessons of COVID-19, and a rapidly growing body of technical research specifically focused on AI alignment, the problem of ensuring increasingly powerful artificial intelligence systems remain reliably beneficial and controllable as their capabilities continue to grow. None of this guarantees humanity successfully navigates whatever filter might genuinely lie ahead of us. The honest, sobering truth is that we cannot currently know with any real certainty whether careful institutional effort, international cooperation, and technical research into risk mitigation are actually sufficient to meaningfully change the odds, or whether the underlying dynamics of technological development make some kind of catastrophic outcome effectively inevitable regardless of how carefully any individual civilization tries to manage it. The same brutal dynamic potentially playing out identically on every other technological civilization that has ever emerged anywhere in the galaxy's long history. But the mere existence of thousands of researchers across dozens of institutions worldwide treating this specific problem as one of the most important, most tractable, most morally urgent challenges facing our entire species suggests that at least some meaningful fraction of humanity has already started taking Fermi's original lunchtime question, and everything Robin Hansen's great filter concept eventually built on top of it, with exactly the level of seriousness it actually deserves. Let's give equal, honest time to the more hopeful possibility, because a fair treatment of the great filter has to acknowledge that the entire framework rests on an assumption that might simply be wrong. The assumption that a truly empty-looking galaxy is even the correct way to describe what we're actually observing. Some researchers have pointed out that our search for extraterrestrial civilizations has been shaped almost entirely by our own specific, narrow assumptions about what alien technology should look like, primarily radio signals and, more recently, hypothetical megastructures large enough to detectably block a portion of their host star's light. An idea explored seriously after astronomer Tabitha Boyajian and her team discovered the strange, irregular dimming pattern of a star now popularly known as Tabby's star in 2015, a signal that generated enormous public excitement before more careful analysis suggested the dimming was most likely caused by orbiting clouds of dust. Rather than any artificial structure, it's entirely possible that a sufficiently advanced civilization would develop communication and energy technology so far beyond our current understanding that we simply wouldn't recognize the evidence, even if it were sitting directly in front of our instruments, the same way a civilization from several centuries ago, however brilliant its individual scientists, would have had no framework whatsoever for recognizing a modern fiber optic cable or a satellite internet signal as evidence of anything at all, let alone evidence of an advanced, thriving technological society. Physicist Freeman Dyson himself, whose name is attached to the hypothetical megastructures we search for, spent much of his later career openly speculating that truly advanced civilizations might pursue directions so fundamentally different from our own technological assumptions, forms of energy use, computation, or even physical existence we simply haven't conceived of yet, that our current search methods might be looking for exactly the wrong kind of signal in exactly the wrong part of the sky. Under this more hopeful framing, the silence we observe wouldn't represent a graveyard of civilizations destroyed by an unavoidable great filter at all. It would simply represent the limits of our own current imagination and instrumentation, a temporary, correctable blindness, rather than a permanent damning statistical signal about our own uncertain future. This possibility doesn't eliminate the genuine, well-documented existential risks we've spent tonight discussing. Nuclear weapons, engineered pandemics, and unaligned artificial intelligence remain real, serious threats regardless of whether other civilizations successfully survived them or not. But it does mean that the specific, chilling inference, the galaxy is silent, Therefore, something usually kills civilizations like ours rests on an assumption that we would actually recognize success if we saw it that remains genuinely, scientifically uncertain and worth holding on to as a real possibility rather than dismissing outright in favor of the darker story. Let's pull everything we've walked through tonight back together, because across this much ground, it's easy to lose the overall shape of the argument, and seeing it laid out in sequence is the only way to really feel the full weight of what the great filter actually proposes. Enrico Fermi asked a simple question at lunch in 1950. Given how old and how vast the universe is, where is everybody? Michael Hart's calculations in 1975 showed that even slow sub-light-speed colonization should have filled the entire galaxy many times over within a small fraction of its total age. Frank Drake's equation in 1961 tried to break the problem into individual probabilities and largely failed to resolve it because too many of those probabilities remained genuine unknowns. Robin Hansen's great filter concept in 1996 reframed the entire mystery around a single, sharper question. Somewhere between dead chemistry and a galaxy-spanning civilization, there exists at least one bottleneck so difficult that almost nothing gets through it, and we don't know if we've already survived it or if it's still waiting for us. The candidates behind us, abiogenesis, the emergence of complex cells, the emergence of intelligence itself, would each be genuinely comforting explanations if confirmed, placing the hardest part of the journey safely in Earth's deep evolutionary past. The candidates ahead of us, nuclear war, engineered pandemics, unaligned artificial intelligence, and climate-driven civilizational strain, are supported by real historical near-misses, documented laboratory capabilities, and serious, expert-level risk assessments suggesting a genuinely non-trivial chance of catastrophe within the coming century alone. Anthropic reasoning, through the doomsday argument, arrives at a similarly unsettling conclusion using nothing but pure statistics and the simple fact of your own existence right now, rather than at some far more distant point in a longer, safer future. And alternative explanations for the cosmic silence, the dark forest hypothesis, the zoo hypothesis, the possibility that advanced civilizations are simply using technology we wouldn't recognize as evidence at all, remain genuinely live, unresolved possibilities that could explain the same observed silence without requiring anyone, anywhere, to actually be dead. Nobody currently knows which of these stories is correct. That is not a failure of tonight's research. It is an honest, accurate reflection of where the actual science and philosophy currently stand. A genuine, still open question sitting at the intersection of astrobiology, existential risk research, probability theory, and cosmology. One of the very few questions in modern science broad enough and important enough to require serious contributions from all four of those fields simultaneously, and specific enough that the answer, whenever it finally arrives, will tell us something permanent and irreversible about our own species' place in the entire history of the universe. So let's bring this all the way back down to something personal, because it would be easy to walk away from everything we've just covered feeling small or helpless or quietly terrified and none of those reactions would actually be useful or, honestly, fully justified by the evidence. Here is the thing about the great filter that almost never gets said clearly enough. Even in its darkest possible interpretation, it is not a prophecy. It is not a countdown clock with a fixed, unavoidable expiration date. It is a statistical pattern observed across a galaxy of civilizations we cannot actually see individually, one by one, to know exactly why each of them failed, if any of them failed at all. We are not passive observers watching a fate play out. We are right now in this specific century the ones actually deciding through millions of individual choices made by scientists, engineers, policymakers, and ordinary citizens, exactly how this particular chapter of the story turns out for us specifically. Every single existential risk we discussed tonight, nuclear weapons, engineered pandemics, unaligned artificial intelligence, climate instability, shares one crucial, genuinely hopeful property. Every single one of them is, at least in principle, a problem human beings can actually influence through better international coordination, better technical safety research, better long-term institutional planning, and better collective decision-making. This isn't a naive feel-good platitude tacked onto the end of an otherwise frightening conversation. It's a direct, logical consequence of the fact that these specific risks, unlike, say, a sudden, unpredictable asteroid impact or an unstoppable natural pandemic with no human origin at all, are risks we ourselves created through our own technological development, which means they are also risks we retain some genuine, meaningful capacity to reduce, manage, and potentially navigate successfully, provided enough people take the underlying problem seriously, but enough, soon enough, and act on that seriousness with real sustained effort rather than treating it as an interesting thought experiment to discuss once and then forget. This is, I think, the actual honest takeaway the great filter offers once you strip away the more dramatic, doom-laden framing that usually surrounds it. It isn't a message telling you the future is already written. It's a message telling you the stakes of this exact moment in history are almost unimaginably high, precisely because nobody, anywhere, including us, has ever gotten a guaranteed pass through whatever bottleneck might genuinely be waiting up ahead. That's not a comforting thought, but it is, in its own strange way, an empowering one, because it means the outcome genuinely depends, at least in part, on what we, collectively, choose to actually do about it. There's a version of this entire question that flips the fear completely on its head, one that philosopher Nick Bostrom has explored under the concept of astronomical waste, and it deserves genuine attention because it reframes everything we've discussed tonight from an entirely different angle. What if the reason the galaxy looks empty isn't that everyone dies before reaching the stars, but simply that nobody has gotten there yet, and we happen to be among the very first? Given that the universe is 13.8 billion years old, and that the kind of stable, long-lived, sun-like stars capable of hosting complex life could plausibly continue forming and supporting habitable planets for tens of trillions of years into the future, dwarfing the current age of the universe by a factor of 1,000 or more, it's entirely mathematically possible that intelligent life is not a common, mature galaxy-spanning phenomenon at all, but an almost impossibly early, almost impossibly rare occurrence, with humanity representing one of the very first sparks of technological intelligence to appear anywhere in the entire observable universe, rather than one of the last survivors of a long line of failed predecessors. If this framing turns out to be correct, the stakes of the great filter shift in a genuinely fascinating way. It would mean humanity isn't gambling against a filter that has already claimed countless victims before us, hoping to somehow beat odds that have already crushed everyone else who tried. It would mean we are simply early, first through a door that will eventually, over the coming billions of years, open for countless other civilizations across the galaxy and beyond, and that whatever choices we make in the coming century about how carefully we manage nuclear weapons, biotechnology, and artificial intelligence aren't just decisions about our own narrow survival. They become, in a very real sense, a kind of test case, a working example that other, later civilizations might eventually study, learn from, or even directly build upon, should we manage to leave any lasting record of how we navigated this exact same narrow, dangerous window successfully. This doesn't resolve the uncertainty at the heart of tonight's entire program, and it shouldn't be mistaken for false comfort dressed up as science. We genuinely do not know whether we're early, whether we're standing on the shoulders of countless failed civilizations before us, or whether we're simply unremarkably alone in a universe that turns out to produce intelligent life so rarely that comparing our situation to any broader statistical pattern doesn't even meaningfully apply. But holding this, we might be first possibility alongside the darker, we might be the latest in a long line of failures, possibility does something valuable. It reminds you that the actual data, the honest, complete scientific picture available to us right now in July of this year genuinely permits both stories, and that choosing to act as though we are early, as though what we do next actually matters for a future far larger than our own individual lifetimes, costs us nothing, and might, if the more hopeful version turns out to be true, matter more than any of us currently have any way of knowing. There's one more idea worth sitting with before we close, and it comes from thinking carefully about what would actually happen to the meaning of the universe itself, depending on how this question eventually gets resolved. If it turns out that we truly are alone, the only conscious, thinking, meaning-making beings anywhere in the entire observable universe, then something genuinely strange follows from that. The universe, in its full 13.8 billion year, 93 billion light-year diameter grandeur, would have no other witnesses, no other minds capable of looking up, measuring a galaxy, naming a star, or wondering, the way we're wondering right now, what any of it actually means. Every photograph ever taken of a distant nebula, every calculation of a black hole's mass, every careful measurement of the cosmic microwave background would represent the entire universe's only chance anywhere, at any point in its existence, to actually be observed, understood, and appreciated by anything at all. That is an enormous, genuinely staggering amount of responsibility to carry, whether or not you've ever consciously thought about it in exactly these terms before. If consciousness, curiosity, and the capacity for wonder really are as rare as some interpretations of the Great Filter suggest, then human beings aren't just one interesting species among countless others scattered across a crowded, chatty galaxy. We might be, quite literally, the only place in the entire universe where the universe has ever managed to look back at itself and ask what it is. Astrophysicist Carl Sagan once described human beings as a way for the cosmos to know itself. And whether or not that phrase was originally meant as poetry or as literal cosmology, the Great Filter forces you to sit with the very real, very serious possibility that it might be describing something closer to a hard, unadorned scientific fact than anyone realized when he first said it. Whether we turn out to be alone or one voice among countless others separated by walls of distance and time we may never fully cross, the actual, practical stakes of tonight's entire conversation remain exactly the same. Somewhere in the next 100 years, humanity is going to make a series of decisions about nuclear weapons, about biotechnology, about artificial intelligence, about how carefully we manage the very tools that could either carry us safely through whatever bottleneck the Great Filter represents, or end the story here, quietly, without any future civilization ever knowing we existed at all. Nobody currently knows for certain which side of that filter we're standing on, but everybody alive today, whether they realize it or not, is currently helping to write the answer. Let's talk, for a moment, about what it would actually feel like to live inside this uncertainty well, rather than letting it curdle into either denial or despair, because both of those responses, understandable as they are, waste the exact clarity the Great Filter can actually offer you if you let it. Denial looks like treating existential risk as someone else's problem, a topic for scientists and policymakers to worry about, while the rest of us go about our ordinary lives, unaffected, unbothered, secure in the assumption that things have always worked out before, so they'll probably keep working out now. An assumption that, if you've been paying attention for the past hour, doesn't actually survive contact with the historical record. Despair looks like concluding that if the odds really are this uncertain, if a documented 1 in 6 chance of civilizational catastrophe within the next century is really on the table, then nothing any individual person does could possibly matter anyway. A conclusion that feels emotionally understandable but is, on the actual math, simply false. Every single one of the near misses we discussed tonight, Stanislav Petrov's decision not to report a false missile alarm, Vasily Arkhipov's refusal to authorize a nuclear torpedo launch, was made by exactly one person in exactly one room, making exactly one choice under enormous pressure, and that one choice measurably changed the entire subsequent history of our species. The existential risk researchers currently working on AI alignment, on pandemic preparedness, on nuclear de-escalation policy, are not a separate, specially chosen class of people uniquely responsible for solving this problem while everyone else watches from the sidelines. They are, for the most part, ordinary people who decided at some point that this particular problem was worth taking seriously enough to actually work on. The same choice available to literally anyone listening to this sentence right now. Whether that choice takes the form of a career, a donation, a vote, a conversation with a friend who's never thought about any of this before, or simply choosing to stay informed rather than looking away. This is, I think, the actual, honest, unglamorous answer to the question the great filter forces you to confront. We do not get to know in advance with certainty whether humanity successfully makes it through whatever bottleneck might be waiting for us. Nobody in the entire history of any civilization anywhere ever gets that guarantee handed to them before they have to act. What we do get, every single one of us alive right now, in this specific, statistically loaded century, is the same basic choice every generation before us has faced in its own particular crisis: to treat this moment as though it matters, and to act accordingly, or to treat it as background noise and hope, quietly, that someone else handles it instead. So let's step all the way back now, past the equations, past Fermi's lunch table, past the doomsday argument and Sagan's cosmic calendar, and land on the single image that started this entire conversation: a silent sky, full of more stars than grains of sand on every beach on Earth, and not one confirmed signal, not one confirmed visitor, not one confirmed trace of anyone else out there, anywhere, despite 65 years of increasingly sophisticated searching. That silence is real. It is measured, documented, and confirmed by some of the most sensitive instruments human beings have ever built. What it actually means remains, after everything we've walked through tonight, genuinely, honestly unresolved. It might mean we are staring at the aftermath of countless failed civilizations, each one climbing the same staircase we're currently climbing, each one hitting the exact same catastrophic step somewhere near the top. A graveyard so quiet and so complete that not even the wreckage survives long enough for anyone to find it. It might mean complex, intelligent life is simply staggeringly rare, a chemical and evolutionary lottery ticket so unlikely that Earth may represent one of vanishingly few winning draws across an entire galaxy of otherwise sterile, lifeless worlds. It might mean we are simply early, the first spark of technological intelligence to appear in a universe still young enough, still fertile enough, to eventually produce countless more long after we're gone, long after anyone remembers we were ever here at all. Or it might mean something stranger still, that the universe is quietly, deliberately full, and everyone smart enough to survive this long already learned exactly why staying silent, staying hidden, and staying patient was always the safer bet. Nobody currently gets to know which of these stories is actually true. What every single person alive today does get to know with complete certainty is that we are living through the exact moment where the question stops being abstract and starts being personal, where the careful, patient work of scientists studying alignment, biosecurity, and nuclear risk stops being a distant academic exercise and starts being the actual ongoing determination of which story about humanity eventually gets told, assuming anyone, anywhere, is ever around to tell it. Go outside sometime soon, somewhere dark enough that the sky actually opens up above you, and look up, not the way you might have looked up before tonight, casually, passively, taking the silence for granted as simply the natural, expected quiet of an empty universe. Look up the way Fermi looked across that lunch table in 1950, genuinely puzzled, genuinely demanding an answer the universe has never actually given us. Somewhere among those points of light on some fraction of that billion potentially habitable worlds scattered across our galaxy alone, the same staircase we've been climbing for the past 4 billion years might be underway right now. Other planets working through the exact same chemistry, the exact same biology, quite possibly the exact same narrow, dangerous window of technological adolescence we happen to be walking through ourselves at this exact moment, completely unaware of each other, separated by distances and delays so enormous that even if every single one of those civilizations succeeds, we may never live to know it. And somewhere among those same points of light, it's entirely possible that other planets already tried, already climbed most of that same staircase, and already, quietly, without fanfare, without warning, stopped. The exact same way, it's entirely possible that we're the very first to have made it this far at all. The stars don't tell you which story is true. They just sit there, patiently, the way they always have, holding the answer just out of reach, exactly the same way they held it during Fermi's lunch, exactly the same way they'll hold it long after everyone watching this video tonight is gone. What changes, if anything changes at all, is not the sky itself, and not the silence coming from it. What changes is you, and whether you carry that silence differently now than you did an hour ago, whether you treat the next century of human decisions about nuclear weapons, about biotechnology, about artificial intelligence, as background noise happening to someone else in some other room, or as the actual undecided answer to the single oldest and most important question our species has ever had the ability to ask out loud. There's one more piece of the puzzle worth understanding before we close, because it gives the entire great filter question a genuinely useful way to measure just how empty the universe actually appears to be, not just in terms of simple radio signals, but in terms of raw energy use itself. In 1964, Soviet astronomer Nikolai Kardashev proposed a framework for classifying hypothetical civilizations based purely on how much energy they're able to harness. A Type 1 civilization would be capable of harnessing all the energy available on its home planet, capturing essentially the entire power output its star delivers to that world. A Type 2 civilization would be capable of harnessing the entire energy output of its home star itself, potentially through a hypothetical megastructure called a Dyson sphere, a vast shell or swarm of collectors surrounding the star to capture its light directly. And a Type 3 civilization would be capable of harnessing the energy output of an entire galaxy, a scale of engineering so far beyond anything humanity has ever attempted that it's genuinely difficult to picture in concrete terms. By this scale, human civilization currently sits at approximately Type 0.7, meaning we don't yet even fully control the energy resources of our own single planet, let alone our star or our galaxy. Here's what makes the Kardashev scale directly relevant to tonight's entire discussion. A genuine Type 2 or Type 3 civilization would likely be detectable at almost any distance, not through deliberate radio broadcasts, which require intentional effort and careful aiming, but simply through the enormous, unmistakable thermodynamic signature of that much energy capture and use, showing up as unusual infrared emissions, unusual patterns of stellar dimming, or other large-scale, difficult-to-hide astrophysical anomalies. Astronomers have actually conducted systematic surveys searching for exactly this kind of signature, most notably the Glimpsing Heat from Alien Technology Survey conducted using the Wide Field Infrared Survey Explorer telescope, scanning hundreds of thousands of galaxies for the specific infrared signature a galaxy-spanning Type 3 civilization's waste heat might produce. The results, published in 2015, found no clear candidates at all, no galaxies showing the unmistakable thermodynamic fingerprint of large-scale artificial energy harvesting on any meaningful scale. This adds yet another layer to the mystery, because it means the silence isn't just about radio waves or even about any single narrow method of searching. It's about the complete absence of any energy signature on any scale we know how to detect, anywhere in the observable universe, consistent with a civilization that successfully made it far enough up the technological ladder to become a Type 2 or Type 3 power. If even a small fraction of the civilizations that ever emerged across cosmic history had successfully avoided whatever the Great Filter represents and gone on to become genuinely advanced, energy-dominant civilizations, we would likely expect to see at least some trace of them by now across the roughly 100 billion galaxies within our observable universe. Finding absolutely none across every method we've tried adds real independent weight to the uncomfortable possibility that whatever bottleneck exists on that staircase from dead matter to galactic civilization, it is genuinely, brutally difficult to survive. It's worth mentioning one final, genuinely recent development, because it illustrates exactly how careful, exactly how slow, and exactly how rigorously skeptical this entire field of research actually has to be before anyone gets to claim a real discovery. In 2024, a team of researchers proposed that the famous 1977 WOW signal might actually have a natural, non-artificial explanation after all, potentially caused by a rare astrophysical event involving a flare from a magnetically active star interacting with a cloud of cold hydrogen gas, producing a brief, intense, naturally occurring radio burst that could plausibly mimic several of the characteristics scientists once considered evidence of an artificial transmission. The proposal remains contested and by no means fully settled, but it's a genuinely useful case study in exactly the kind of patient, self-correcting scrutiny that separates real science from wishful thinking. Nearly 50 years after the signal was first detected, researchers are still actively working to explain it, still refusing to simply accept the more exciting interpretation without exhausting every plausible, mundane explanation first. This pattern, promising anomaly, careful investigation, eventual reassignment to a natural cause, or in rarer cases, genuine confirmation, describes essentially the entire history of the search for extraterrestrial intelligence. And it's exactly why, after 65 years of dedicated searching, we still don't have a single confirmed detection to report. It would be easy to read that as evidence the whole search is futile, or that the entire question of the Great Filter is unanswerable speculation dressed up as science. It's actually closer to the opposite. The fact that researchers keep returning to old data with new tools, keep proposing and testing new hypotheses, keep building bigger telescopes and more sensitive detectors specifically to chase down a single 4-decade-old radio anomaly tells you something genuinely admirable about how seriously this question is actually being treated by the people who study it professionally, even when, especially when, the honest answer, after all that effort, remains we still don't know. If tonight changed even slightly how you think about that silence the next time you find yourself under a genuinely dark sky, that's exactly what this was for. If you'd like more evenings like this one, spent carefully, honestly walking through the deepest, strangest, and most genuinely consequential questions modern science has ever raised, consider liking this video or subscribing to the channel. It costs you nothing, and it helps this kind of long, patient, actually substantive exploration find its way to more curious minds who might need exactly this kind of perspective tonight. The same way Fermi's simple lunchtime question eventually found its way decades later to an economist named Robin Hanson, who turned it into one of the most quietly important ideas in all of modern science. An idea that, as far as I can tell, still hasn't received anywhere near the widespread public attention its actual implications genuinely deserve. There's one final, genuinely cutting-edge piece of this story worth including because it comes directly from the same economist who coined the term great filter in the first place. And it represents one of the most creative, most mathematically rigorous attempts yet to actually resolve the entire paradox. In 2021, Robin Hanson, along with several collaborators, published a detailed model they called Grabby Aliens, built around a genuinely clever piece of statistical reasoning. If advanced civilizations eventually expand outward from their home star at some significant fraction of the speed of light, visibly and permanently transforming every star system they pass through, then any civilization young enough to still be looking up at an apparently untouched, natural-looking night sky must, by definition, be looking at a universe where no expanding, grabby civilization has reached their location yet. Using the timing of when such civilizations could plausibly first appear, combined with the simple fact that we currently observe an apparently untouched sky, Hanson's team calculated a specific, testable prediction. Humanity likely exists at a very particular, statistically expected point in cosmic history, one where grabby civilizations are just beginning to appear across the universe, expanding outward and likely to become visible, transforming visible portions of the night sky within the next few 100 million years. What makes this genuinely different from most Fermi paradox explanations is that it isn't just a story. It produces an actual falsifiable prediction about when humanity should expect to eventually see direct evidence of expanding alien civilizations altering the visible universe, a prediction other researchers can test, critique, and refine using future astronomical surveys. It also offers a strange, almost vertigo-inducing possible resolution to tonight's entire question. Under the Grabby Aliens model, the reason we don't see anyone yet isn't necessarily that a great filter killed almost everyone before us. It might simply be that visible, galaxy-transforming expansion takes a very specific, very long amount of cosmic time to become detectable, and we happen to exist at almost exactly the right moment, statistically speaking, To be among the very last generations of any civilization anywhere that gets to look up at a sky still empty enough to ask Fermi's original question at all. And the next time you look up at the stars, remember that the silence you're hearing isn't empty. It's loaded, dense with possibility, holding at least 4 or 5 genuinely different explanations for why an old, vast, fertile universe appears, as far as we can currently tell, to be almost completely alone. We might be looking at a graveyard, a galaxy quietly littered with the remains of civilizations that climb most of the same staircase we're climbing right now and never made it to the top. We might be looking at a nursery, a universe still young enough, still early enough in its own long story. That intelligent life simply hasn't had time yet to spread and announce itself in any way we'd currently recognize. We might be looking at a crowded room where everyone learned, the hard way or through careful reasoning we haven't discovered ourselves yet, that staying quiet was always the safer bet. Or we might simply be looking at the honest limits of our own instruments, staring at a sky that's actually full of answers we simply haven't learned how to hear yet, using tools too young and too narrow to catch signals from technologies we can't even imagine. Nobody currently knows which one is true, and that not knowing, held honestly, without flinching away from it and without collapsing into despair over it, might be the single most important thing you take away from tonight's entire conversation. We just do our best, from right here, on this one small, quiet, statistically loaded planet, in this one narrow, decisive century, doing what we can to make sure that whichever story turns out to be true, it's a story someone, somewhere, eventually gets to finish telling. Good night, and thank you sincerely for spending part of this exact, narrow, decisive moment in cosmic history thinking carefully about a question most people never let themselves fully sit with at all. Whatever the actual answer turns out to be, whether we are early, whether we are alone, whether we are simply the latest attempt in a long, silent line of civilizations that came before us and never made it past this exact point, the honest, careful act of asking the question at all, the way Fermi asked it over lunch in 1950, the way Hansen reframed it in 1996, the way researchers are still refining it today with grabby aliens and gamma-ray surveys and infrared telescopes scanning for waste heat from civilizations that may not even exist, is itself a small act of defiance against the silence, a refusal to simply accept not knowing as a reason to stop looking, stop measuring, and stop caring about what happens next. Every measurement, every equation, every documented near miss we walked through tonight, from Petrov's midnight decision in 1983 to Hansen's grabby aliens model published just a few years ago, was built the same patient, careful way, by people willing to sit with genuine, uncomfortable uncertainty long enough to actually learn something true from it, rather than reaching for whichever answer felt most comfortable, most reassuring, or most immediately satisfying, and simply stopping there, the way it would have been so easy and so understandable for any of them to do. That patience is not a small thing. It is, in its own quiet way, exactly the kind of trait a species probably needs if it genuinely hopes to make it safely through whatever is actually waiting on the far side of that staircase Whether the great filter turns out to be behind us, ahead of us, or, in the strangest and perhaps most hopeful case, simply a question we're still early enough, still young enough, still fortunate enough to be the very first civilization anywhere to ever properly answer. Good night, and I'll see you out there, somewhere between the staircase and the stars, still looking up, still asking the question, still refusing, patiently and deliberately, to let the silence have the final word. Thank you, truly, sincerely, deeply, and warmly, for staying so genuinely curious about all of this.